welcome to this segment of the Math Coach. Today, we're going to take an in-depth look at unit number 3, exploring linear relations. But before we do that, I'd like to give a big shout out to my crew at Explain Everything, who have provided us with such an amazing app that even you can use for your school presentations. Now, let's get started. So let's go over the first page here, and I'm just going to remind you guys of a few things. How to graph. Remember that this axis right here is your x-axis. Okay, so that's the first column right here. These are your x values right here. And then on the second column are your y values. And that is your vertical axis right here. So your y is this axis right here. And your x is this axis right here. Okay, you don't have to highlight this in a different color. I'm just doing that so you could see me do it. And now to plot every point, remember how you plot every point. So we're going to take the first point, and I'll plot all these points in green, but the first point says 123 for x and 350 for y. Now, just understand that your x values are going up by increments of 15. So you have to ballpark where 123 is. 123 is somewhere right there, closer to the 120, obviously. And notice that your y values are all going up by increments of 30. Okay, so 350 for y is going to be somewhere in here. All right. So 123 for x and 350 for y. So I'm going to have to ballpark this. And I'm going to say that this will probably be somewhere around there. That point right there. The next point, 120, 300. 120, 300. Now I don't have to ballpark 120 for x. There is a 120. So right here. So 120 and 300. 300 for y is right there. So 120, 300, where those two things meet, x and y, that is where that point is. So I got 2 points so far, there and there. The next point, 175, 250. So I've decided to extend the graph because it wasn't at 175. So now 175, 250 is somewhere about here. Okay, so that should be one dot. The next point, 78 to 22, right about here. The next point is 124, 157, right about here. Next point is 75, 128, right about here. Next point, 1727, right about here. Next point is 1850, right about here. Then 4871, right about here. 6275, right about here. 3876, right about here. 4886, right about here. 47100. Right about here. 52, 100, right about here. 51, 120, right about here. 56, 120, right about here. 55, 127, right about there. 70, 150, right about there. These green dots are called a scatter plot. Okay, and a scatter plot is just a set of dots, and it's measuring two things. In this case, we're looking at the wingspan of the birds in comparison to their length. So here's the length of the bird, and here is the wingspan of the bird. So they took, for instance, the first bird. They know that the length of that bird is 123 centimeters, and then they measured their wingspan as well, and the wingspan is 350 centimeters. The questions that arise here right now, nothing too crazy here, but it says to describe the pattern of the dots on the scatter plot. And the pattern of the dots on the scatter plot, as you can see, I can actually draw what is called a line of best fit. And the line of best fit follows the direction the dots are going, and it tries to pass through as many dots as possible, has the same amount of dots on both top and bottom of the line. This here would be a pretty good line of best fit, although everyone's will look a little different, but you try to go through as many points as possible and have the equal amount of points on the top of the line as is on the bottom of the line, and all the dots have to be just as far away from each other as the other ones. By that I mean that if you take a look at this green dot right over here, that green dot there, it's on top of the line, and this green dot there is below the line, and they're pretty equally spaced, equally far away from that red line. Same with if I took a look at this green line, this green dot here, and this one here. I mean, this one is about that far. This one is probably the same or pretty close to the same distance away from the line. So you want to try to have the same amount of points on the top as there are on the bottom. They cancel each other out, and as many points on the line as possible. Everyone's line of best fit is going to look a little different. If we have a machine to do it, a computer, a graphing calculator, then the graphing calculator will always draw the line of best fit proper. We'll speak more about this later, but let's take a look at the relationship here. This is actually called a positive correlation. Okay? Why is it a positive correlationship? Well, it's increasing. This red line is increasing up and to the right. If it's increasing like this, because we always read from left to right, so the line starts low and goes high, right? So if it does that, then we know that it is a positive correlation, meaning it is increasing. So that's why we're going to write that there. And it asks us to describe the relationship between the bird length and the wingspan. So I said, as the length increases, the wingspan also increases. Because as my length is going forward or higher, the wingspan is getting higher. This thing is going a positive correlation. So as the x-axis increases, so does the y-axis. Speaking of correlation, if we go to page 6 in your package, it says scatterplots type of correlation. So it speaks about positive and negative correlationships. So this first one right here is much like the one that we just did. This here is a positive correlationship because this line is going up and to the right. If we were to draw a line of best fit, and if you were to take a ruler and actually draw a line of best fit, you're going to get something that looks like this. And we can see when we read this from left to right, this is increasing. It's going up and to the right. This is a scatter plot, shows a positive. This is a positive correlation when the pattern rises up to the right. This means that the two quantities are increasing together. If we take a look at the next one, this one right here, we can see that this is the opposite. If we were also to draw a line of best fit for this, and I'll take out my ruler here as well, if I were to draw a line of best fit, it would look something like this. And we could see that this is going downwards. If we read from left to right, this is going down and to the right. This is a scatter plot, and it shows a negative. This is a negative correlationship when the pattern falls down to the right. This means that as one quantity increases, the other one is decreasing. Now, let's take a look at this as well. This is very important. Strong or weak correlationship. So is it a strong correlationship or is it a weak correlationship? What do they mean by that? Well, the closer that the points are to becoming a line, the stronger it is to being a linear relationship. For instance, once again, I'm going to take out my ruler, and if I were to draw a line of best fit on the first one that you see here, you can draw a line. Now, this is positive correlationship, but you can draw a line that goes through almost every single point. This is actually very strong. If the points nearly form a line, then the correlation is, and I'm going to say that it is strong. So this is strong. To visualize this, enclose the plotted points on an oval. If the oval is narrow, then the correlation is strong. If we take a look at the next one, and again, I'm going to take out my ruler here, and I'll draw it in red. If I were to draw a line of best fit here, I'll do my best here trying to go through as many points as possible, equal amount of points on the top and the bottom. It's not a perfect line, okay? A perfect line means 100% strong. The last line that we just drew right here, I mean, how strong is that? It's pretty close to 100% strong. If it's exactly a line, it's 100%. This is probably, I would say, like 95, 98% strong. Anywhere between 95 and 98 would be pretty acceptable. So I don't know. Some of you may say 96% strong. Some of you may say 98. Then that's fine. It's not 100, but it's very close to 100% line. Now this red line, on the other hand, it's pretty strong as well. I mean, most of those points are pretty close to that line, but it is not 100%, and it's probably not 90%. I mean, it's probably somewhere around 80% or 85% strong. So if you guess anywhere between there, I mean, that would be a pretty good guess. How close is it to being a line? And so we would say that this is fairly strong. Okay? It's not as strong as the last one, but it's fairly strong. Okay? If the points, the last one, and I'll draw the last one in blue, and I will also get my ruler out for this, and if I were to draw a line of best fit on this one, you can see that these points, although I've passed through as many points as I could, these points are pretty dispersed. They're still going down and to the right. We know that it's going this way, but it's definitely not 100% aligned, okay? These points are not even 80% aligned, because if we suggested that this is 80, then, you know, what's this one? How close to a line are those points? And, you know, it says if the points are dispersed even more widely but still form the rough pattern of a line, then the correlation is moderate. So I would say that this one is moderate. Sometimes it's even worse than moderate. I mean, the further away these points are from a line, the worse the correlation coefficient is. Okay, so to be strong or weak, I gave you an example of, you know, it's getting closer to being weak right there, but it's moderate still. This one's fairly strong still right here. This one is very strong. And let's take a look at the last one, because on your book, it has one that has no correlation whatsoever, or a very weak correlation. So what would that look like? So this would be an example of no correlation right here. This is no correlation because you can't possibly draw a line of best fit. I mean, we don't know the direction of this line of best fit. Should the line of best fit go this way? We don't know. That's, you know, this is not even going in a direction. Should the line of best fit, I'll take out my ruler here again, and should it go this way? I mean, we don't know. There's no direction to these points. We don't know where to draw the line of best fit. So you can't draw one. This is very, very weak. So we would say that this is extremely weak or weak. Okay? And how close is this to a line? I mean, this is like 0% close to a line. It's not anywhere close to being a line, so it is definitely not linear whatsoever. So we're going to try a line of best fit question on page 7. It says, to be able to make predictions, we need to model the data with a line or a curve of best fit. So rules for drawing a line of best fit. The line must follow the points. Okay, so the first rule is that they must follow all of the points, the direction of the points. The line should pass, okay, so it should pass through as many points as possible. There should be the same number of points above and below the line. So it should be this, there should be the same number of points above and below the line. It also says that the line should pass through points all along the line, okay, not just at the ends. Okay, so it's not necessarily the ends, it's got to pass through as many as possible. So I'm just going to delete this part here, and then I am going to zoom in on the picture of what we're doing. It says use the information below to draw a scatter plot. Describe the correlation and draw the line of best fit. Okay, so the question actually says the teachers at Holy Mary High School took a survey in their classes to define if there is a relationship between the students' marks on a test and the number of hours watching TV the night before. So they have two things here that they're measuring. They're measuring the marks on their tests and the number of hours that they watched TV for. Okay, so what axis are we going to call X and what axis are we going to call Y? Remember, this is the X axis. And we know that this is the y-axis. Well, they've told you that the first thing that they're measuring is the marks on the test. So that will be this axis right here. Marks on the test, this will be the x-axis right here. And the y-axis, the numbers that go on the y-axis will be this over here, the number of hours. Okay, because it says they want to know if there is a relationship between the student's mark on a test and the number of hours. So they want it in that order. So we got to make sure that we appropriately value the y-axis and the x-axis. So I've decided to look at the y values first, and I can see that the lowest value that I see for y is 1, and the highest value I see is 4.5. So I got to definitely catch all those values on my y-axis. So I actually started here at 0, okay, and then every second tick is 1, then 2, and so forth. Okay, every second tick is a 1, and so that means in between would be a 0.5, right? Then if I look at my x values, I mean the lowest is going to be 0, but let's take a look at the actual lowest values on my x-axis. If you look through all of these points here on the x-axis, the lowest value that I see in my x values is 55. And the highest value that I see in my x-axis is 85. So I got to make sure that I catch 50 from 55 all the way to 85. How am I going to do that if I start with 0 here? You know, I can't go up by increments of 1, 2, 3. You know, I can't even go up by increments of 10, 10, 20, 30. By the time 40, 50, 60, 70, 80, 85, 90. I mean, I could technically go up by increments of 10 if I wanted to, but I'm going to actually do something a little different. What I've decided to do is go up by increments of 10, but I've decided to put this symbol here. That symbol here means a break, okay? It's very important that you have a break if you do what I did here, because the first tick says 55. You cannot have 0 here and then 55 next unless you have that break, because then I go up by increments of 5, 60, 65, 70, 75, and so forth. Okay, so I'm going up by increments of 5. This is why I have this break here. I have this break on purpose there to indicate that there is a break in the x-axis, and then I'm going up by increments of 5. But I'm going to start at 55 because I don't have any numbers that are smaller than 55 actually. All right, so let's actually plot the points now, and I will plot the points, let's say, in green. So if I plot the points in green, let's take a look at the first point. The first point gives me 75 for x and 1. So 75, 1, that's right there. The next point is 70 for x and 2 for y. So 72 is right here. Then I have the next point is 68, 3. We'll have to ballpark the 68. So 68, 3 is somewhere around here. Then we have 73, 2. Again, we're going to have to ballpark the 73. So 73, 2 is somewhere there. Then I have 59, 4. So 59, 4 is somewhere there. I have 57 and 4.5. So 57 will have to ballpark, but 4.5 will be right at that line right there. I have 80 and 1. So 80 and 1 is right here. I have 65 and 3. 65, 3 is right here. I have 63 and 3.5. 63 for x will have to ballpark, and 3.5 for y is right there. Then I have 55, 4. So 55, 4 is right there. I have 85, 1. 85, 1 is right there. I have 70 for x and 2.5 for y. So 72.5 is right there. And then the last point I have is 55, 4. So 55, 4 is actually the same point as what I had before. I had 55, 4 there, and I have a 55, 4 there. So you got to be careful here because there are 2 points there. So how are we going to indicate that there are 2 points at that 55, 4? Because we have to take that into consideration. So what I'm going to do is I'll take a different color and circle it. A different color and circle it like that. I circled it in black. And I'm indicating that there are 2 of those points there. Okay, so there's 2 points that are the exact same. Okay, so I have to take that into consideration. Now let's draw the line of best fit. Now I'm going to draw the line of best fit in red. So I'm going to take out my ruler here, and we have to draw a line that, remember, goes the direction of all the points. Okay, we want to go to the direction of all the points, and we want to try to pass through as many points as possible, leaving the same amount of points on the top and below the line of best fit. And it doesn't necessarily have to go through the end points, the one at the beginning, the one at the end. So we're going to do our best. I mean, everyone's is going to look a little different, but I can tell you that you should have a line of best fit that is going down and to the right. And that's the way I drew mine right there. I mean, it goes through 3 points, and you can see that there are, I'll count them out here. There are 1, 2, 3 points above the line, but then there are 1, 2, 3, 4, 5, 6, and there's another one, 7 below. So this actually is not a very good indication of what the line of best fit is. So I'm actually going to redraw this. So I've decided to redraw the better one in blue. You're going to see the difference between the blue one and the red one. See, the blue one, if you follow the blue one across, you're going to see that the blue one actually goes through a few more than what the red one went through. Okay, so the blue one goes through 1 point here. Okay, goes through another point right there. It goes through another point right there. And it goes through another point right there. So it actually goes through 4 points. And then if you take a look at how many points are on the top of the blue line, I have one that's pretty close actually, 2, that's pretty close. 3, that one's also pretty close to the blue line. And then 4, that's a little further away. Then on the bottom I have 1, 2, 3, and then I have 5 below. I mean, you're going to have sometimes that one more below than on top, but this is way better than the red line. I mean, the red line's still okay, but I would think that the blue line went through more points. It was closer to more of the points, and there's almost an equal number of points on the bottom and on the top of that blue line. Let's answer some questions though that weren't asked. Number one, what type of correlation is this? It's a negative correlation. It's negative correlation because if you look at the negative correlationships, it goes down and to the right. Okay, so it goes down and to the right. And so we know that as these numbers of x get bigger, the y values get smaller. Okay, so as the marks get higher, so this is the way we could say it, because we know that marks are the x-axis. So we got the marks on the x-axis, and we got the number of hours watching TV on the y-axis. So we could put this into a sentence, okay? Because as the marks get higher, the number of hours watching TV is lower. So that's what I wrote here. As the marks increase, as the marks are getting higher, the number of hours watching TV decreases. So as the marks get higher, the number of hours watching TV gets lower. What's the strength of this correlationship? I mean, those green dots are pretty close to that blue line. So I would probably say that this is not strong, but fairly strong. How strong is it? I mean, it's definitely not 100% a line, but it's pretty close to a line. So, I mean, some people may guess about 80%, 85% close to a line. There's no way to really tell unless you have an actual machine, such as a graphing calculator.
We interrupt this program to bring you...
What? Shorty wanna ball with the team.
When you're running around hitting people and making plays, and that's just something that I just loved. It spoke to like this other side of me. I love math because if you ask yourself what language describes the world we live in a quantitative way, the only answer is mathematics.
So let's turn to page 9, and if we look at Julie's height versus her age, you can see that it asks you here in question A to label the vertical axis, then describe the trend of the data, then to describe the relationship. Well, we can already see that they have labeled the x-axis. The x-axis is always the horizontal axis, and the x-axis in this case is your age. And then the y-axis, that's the one they didn't label. So they have this one already labeled, okay? That is your x-axis, your age. Your y-axis is what you have to label, and we know that the y-axis is your vertical axis here. So we're going to label this. And I've labeled it height in centimeters, okay? So this is going to be my y-axis. Now, they've already plotted the points for us, like they've plotted this point already. 170 is right there. 282, they've ballparked the 82, but it's right there. 393, it's right there. So we actually don't have to go and plot any of these points. However, we have to recognize what these points make, describe the trend, describe the relationship, and we're actually going to draw the line of best fit as well. So I pulled out my blue pen and my ruler, and I've drawn this to be my line of best fit. Now, why did I draw this to be my line of best fit? It looks like it passes through one, there's a point there, there's a point there, there's a point there. There's 4 points pretty much on that line, okay? And then there's a couple of points just below this line, and it's almost touching the line, and there's 2 points on top of the line. And they're pretty much touching the line as well. I mean, this is definitely the description of this would definitely be linear, and it is definitely a positive correlation. So I've answered those two. Now, how close to this is a line? I mean, I would say that that line is like 99% accurate, even anywhere from 95 to 99. If you guessed any of these numbers, 99, 98, 97, 95, 96, those would be pretty good indication of how close that is to a line. I mean, it's not 100%. We know that because it doesn't pass through every single point, but it's pretty close. It's pretty close to 100%. I'm also going to answer these other questions that are located on that page. It says variables. The independent variable, okay, so the independent variable is always located on, and in this case, it's always located on the x-axis. This is always going to be the independent variable. The dependent variable, this does not depend on the other variables. So the age doesn't depend on height. It's the other way around. Height depends on age. So this is dependent. Okay, so the y-axis is always your dependent variable, and the x-axis is always your independent variable. Then on the next page, it has this little chart here. So let's answer this chart here. It says, use your line of best fit to estimate the following. So we're going to estimate these things. So it's going to give us a question, and again, we are estimating. We're not going to look at the table of values. We are estimating. So here's the question. So let's take a look at this. So question 1 asks us, how tall was Julie when she was 5 years old? So we're going to have to look at 5 years old. So this is 5 years old. Now we're using our line of best fit. So it has to be on our line of best fit. It's got to be on the blue line. Our blue line is what we're using to make our prediction. Okay, not the actual dots. So if we go up and we look at the blue line, I mean, there it is. This is how tall she was. And we're going to estimate that to be somewhere a little closer to 110. But less than 110, but bigger than 100. I don't know, probably 106. I mean, that's what it is. And that dot actually is 5106. So I'm going to write 106. Okay? So the method of prediction, we used the line of best fit, but there was actually a point there. Okay? So we used the line of best fit, but there was actually a point on that line. Now let's look at number 2. Okay? And how tall will Julie be when she's 9 years old? Okay, so we're going to look at 9 years old. Now, understand, I want to talk about a couple things here, because understand that the data that's given to us, the data is given from age 1 all the way to age 8. So they talk about her height from age 1 all the way to age 8. Anything within that information from age 1 to age 8, so if we're looking from age 1 to age 8, this is called actually interpolation. And it's called interpolation because it is within the data that they give us. They give us data ranging from age 1 all the way to age 8. That's the only data we have on this girl, Julie. If they talk about anything outside of 1 to 8, so I'm going to just write outside, okay, outside of 1 to 8. So if they talk about under 1, so at 0, at 9, at 10, at 11, at 12, any of that stuff is actually called extrapolation. And it's called extrapolation because it's extra information that is not given. So inter is in between the ages they give us. They give us between ages 1 to 8. So anything that we're predicting within age 1 to 8 is interpolation. Anything extra or outside of 1 to 8, so if they ask you before 1 or if they ask you after 8, it's extrapolation. So going back to question number 1, that would be an interpolation question because it's asking us how tall was she when she was 5 years old. I mean, we already have information from 1 to 8. And in question 2, it's asking us how tall will she be when she's 9 years old. 9 years old happens after what they've given us. So we have to ballpark that. We have to estimate that. That is something outside of the information, which is extrapolation. So if we look at 9, okay, and we go all the way up to the blue, and we highlight this point right here, and we come across, and we see how tall she should be according to this data. I mean, at 9 years old, she should be less than 150, but bigger than 140. It's not halfway between. I would say somewhere about 143. So 143 centimeters. And how did we predict that? I mean, we used the line of best fit. Okay? We used the line of best fit. That's what we used. So we use the line of best fit, and it's extrapolation. It's afterwards. So this is using the blue line to make a prediction. Now let's take a look at number 3. Number 3 says, how old was Julie when she's 100 centimeters tall? So we actually have to go backwards here. We have to look at the 100 centimeters tall, which is right there, and work our way across. And it's right, it touches the blue line right about there. So if we go down and make a prediction, I mean, it's somewhere in between 4 and 5 years old. So, and you could tell because you know that at 4 years old, she's 98 centimeters. At 5 years old, she's 106. So I would say, if I had to estimate, I would say that it's just after 4 years. It's not 4.5 years, maybe 4.25 years. You can 4.3 years. I don't know. I'm going to estimate 4.25. Okay, so that's what I'm going to write. I'm going to write 4.25 years. She's 4.25. And how do we use that? We use the line of best fit again. I'll just write line instead of writing line of best fit. So we use the line of best fit as well. Okay, so let's take a look at the last question here, question 4. It says, how tall was Julie when she was born? Well, that's a good question. We don't know. It doesn't give us that information. It actually just tells us at 1 year old. So we have to obviously ballpark that using our line of best fit. We want to know at age 0, how tall was Julie? I mean, if we extend this blue line, it looks like it's somewhere in between, just above 60. It's between 60 and 70, but very, very, very close to 60. So I'm going to say around 61, 62, probably 61. And how did I figure that out? I used the line again. I used the line of best fit again. And once again, this is also extrapolation because this is outside of the data. Okay? So the things that were extrapolation in this case was the last question, was asking us at age 0, and this question here, question 2, was asking us at age 9. Those are both things that happen outside of the data given. Whereas question 1, you know, how tall is she at 5 years old? I mean, we already have that. It's information, it's within the information, so it's interpolation. Same with the question 3, actually. Question 3 is also interpolation. Question 3, it's asking us what age was she when she was 100 centimeters tall, and that's inside of the data as well. She was around 4.25 years old. So we're going to take a look at interpolation and extrapolation, as it's said on the next page. So it says interpolation and extrapolation. Okay, so interpolation and extrapolation. So it says interpolate. So when you're interpolating, you interpolate when you are making a prediction within the data. Okay, so it's within, in the last question, within ages 1 to 8. And you could see the little hint right there. It says, hint, you are interpolating when the value you are finding is somewhere between the first and last point. In our last question, it was in between ages 1 to 8. Okay, so anything between ages 1 to 8 was interpolation. Now, these predictions are usually reliable. Okay, they're reliable because they happened within the data already given. Now, extrapolation is a little different. Extrapolation, we did 2 of those. Extrapolation is when you extrapolate, you are making a prediction outside of the data. Okay, so it's extra, so outside of the data. Okay, and there's a little hint here. You are extrapolating when the value you are finding is before the first point or after the last point. This means you may need to extend the line. And so it says it often requires you to extend the line. Okay? So just like when it asked us, hey, how tall was she when she was born? So that was age 0. So that was before 1 to 8. And then, hey, how tall is she when she was age 9? That was after that 1 to 8. So that's why it was extrapolation. These predictions are always less reliable because they are guesstimates, estimates using your line of best fit. So let's find this question on page 12 of your package. It says, forensic analysis. The question states, anthropologists and forensic scientists use data to determine information about people. Scientists can make predictions about the height, age, and sex of the person they are examining by looking for relationships in large amounts of data. Number 1, construct a graph of the length of the humerus bone versus the length of the radius. Now, I'd ask you to look those 2 things up for science. However, even if you didn't know what those things were, you could still graph this. This is not a big issue. So let's take a look at what we're going to label X and Y. So X, we're obviously going to label as the length of the radius, okay? So length of the radius, and we're going to name that X, and that is in centimeters, okay? Your Y-axis will be the other one, the length of the humerus in centimeters. That is your Y-axis. And we're going to have to figure out what the increments are that we're going up by. I mean, this is always 0 for X. If we don't want to go up by 1s or 5s or 10s, we could always make a break. So let's take a look at the lowest and the highest numbers for X. I mean, the lowest number for X that I see is 21.4. Okay? And the highest number that I see for X is 25. So we're going to try to, make these ticks going from 21.4 all the way to 25. So I'm going to give you a second to look at how you should space it out. So I've decided to start at 0. However, I have a break indicated by this little squiggly line there. So there is a break here. And then I actually made my first number 21. And then I'm going up by increments of 0.4. So this is actually 21.4, then 21.8, and then this is 22.2, 22.6, this is 23, 23.4, this is 23.8, and then this is 24.2, and then this green line is 24.6, and then 25. So this x-axis was very tricky. What we want to try to do is we want to try to use the entire x-axis so that you space out the numbers pretty accurately. Notice this break was very, very important to have this break here so that we can do that. Now let's look at our y-axis. Again, starts at 0, but do I have to make breaks? Well, let's take a look at my y-axis. The lowest number that I actually see here is 23.8, and the highest number that I see here is 29.7. So I'm going to let you, I will suggest make a break here as well. Okay, I'm going to let you make a break, and then I'm going to let you come up with the scale here. I'll give you a couple minutes so you can press pause. So this is what I came up with, again trying to take advantage of this entire y-axis. My lowest number is 23.8. Then I go up by increments of 4. So this is going to be 24.2, then 24.6, and then 25, 25.4, 25.8, 26.2. I'm only labeling every second one. And then I have 26.6, then 27, 27.4, 27.8. Then I have 28.2, 28.6. Then I have 29, 29.4. And then I have 29.8, which is the top. Okay, so I've made use of everything. This will really zoom in on what this looks like. So I'm going to put these points in red, and let's take a look at actually labeling these points. So the first point here is 25, 29.7. So 25, 29.7. It's right about there. Then the next one, 22, 26, somewhere there. Then 23.5, 27.1, right about there. Then I have 22.5, 27, right about there. 23, 28, right there. Then I have 22.6, 25.2, right there. 21.4 and 24, right there. 21.9, 23.8, right there. 23.5, 26.7, right about there. Then 24.3, 29, right there. And then 24, 27, right there. So that is the outlook, the outcome of all my scatter plots. So number 2A says, draw the line of best fit. Okay, so draw the line of best fit. And then 3, if the point on the graph that represents the data for a radius that is 21.9 centimeters long, how long is the humerus? So we're going to answer that based on our line of best fit. So I'm going to try to draw this with a ruler, and this looks like it's going that way up and to the right, but I have to draw it in between these points, passing through as many points as possible where I have as many points on the top and the bottom of my line of best fit. I'm going to try to draw my line of best fit with a ruler using a blue line here. Well, this is how I drew my line of best fit. Now my line of best fit actually only goes through one point. It goes through only one point, and I'll tell you why that does that. So it only goes through this point here. It doesn't go through any other point, but I saw this as going through as many points as I possibly could, where this line is right down the middle of all the points. Same amount of points on the top and on the bottom. I mean, if I had to communicate my idea why I did this, I would suggest that I would say something like this. Like, this point here is above, and it cancels itself out with this point here that's below. See, this one's that far, this one's almost as far from that line. Then this one here is above the line, but this one here is below the line. So again, those two kind of cancel each other out. Then I take a look at this point here. It's almost touching that line, and so is this one. So those kind of cancel each other out. Then I look at this one. This one's pretty far from the line. Probably equal distance or very close to equal distance as that one. This one kind of cancels out with that one. So that's why I chose this to be the line of best fit, because it accurately describes the pattern of the dots. It's going up to the right, so it is a positive correlationship. It went through as many points as possible, which is only one, and it has the same amount of points on the top as on the bottom. Now, it's important to understand what line of best fit actually means. Line of best fit is what accurately describes all of this situation. So we have to kind of erase from our minds. Don't erase it from your page, but I'm going to erase it from my screen here. I'm going to erase all these points from my head, and I'm going to pretend like those points don't exist. The only thing that exists for me is this line of best fit. This is what the data, what represents the data the best. It wasn't exactly a line, but this is what represents that data the best. Now we can answer the questions associated with this blue line. I'm going to answer everything with this blue line only. Okay, so it says if the point On the graph that represents the data for a radius of 21.9 centimeters long, how long is the humerus? So what I'm going to do is I'm going to find 21.9 centimeters long on my x-axis for my radius, because that's what radius is. And if I follow that red line all the way up at 21.9 centimeters, I get that the humerus should be going across 24.8 centimeters. That's my estimate using the blue line only, because that's the line of best fit. I am not going to use any of this stuff over here, because that stuff is irrelevant. I only should use the line of best fit to make predictions. So let's answer some of the other questions. Question number 4. If we look at question 4, it asks us if the point on the graph that represents the data for a humerus, that's very important, that is 27.1 centimeters long. How long is the radius? So it's giving you the humerus. Remember, this is the axis for the humerus. So we have to find 27.1 for the humerus and figure out what the associated length for the radius is on that blue line. So 27.1 is somewhere around here. Okay, so if I follow this all the way to the blue line, it looks right about there. Okay, and then if I go down, I could see that that's associated with the number 23.4. So it's very important that you are looking at the blue line to make predictions. These are both interpolations because this is within the data, inside of the data. This wasn't outside of the data. It asks us to describe the trend next. And the trend in this case, it's a positive correlation. Okay? It's positive because both things are increasing. As the length of the radius increases, so does the length of the humerus. Also, you can say it's linear, but is it strong? I mean, those points weren't too close to the line, so I would say it's moderately strong. Okay, that's what I would say. It's moderate strength. And so question 6 asks me, of course, about describing this in terms of the pattern that's happening here. And the pattern that's happening here, it says describe the relationship as length of the radius gets longer, the humerus also gets longer, because it's a positive correlation. Both things are increasing. Then B states use the line of best fit to predict the length of the humerus if the radius is 24.5 centimeters long. Again, making another prediction. It's asking us if the radius, so if the x-axis is 24.5 centimeters long, what is the length of the humerus? So 24.5, we'll have to look that up. 24.5 is somewhere around here. So if we go all the way up to the blue line and make our prediction, our point is right about there. And we can go all the way across and make our prediction. And it looks like it's just above 28.6. So I would say that it's 28.7 centimeters would be the humerus. Did you interpolate or extrapolate? Well, is this 24.5 within my data or outside my data? So I'm going to refer back to my table of values. And when you look at the table of values, I just popped it back up here on the screen, 24.5. 24.5 is within this data because the radius, the lowest radius we have is 21.4 and the highest radius we have is 25. So anything from 21.4 all the way to 25 is interpolation. Anything outside that would be extrapolation. So this is interpolation. Last question, C, Ask us to use the line of best fit to predict the length of the radius. So we want to find the length of the radius if the humerus is 25 centimeters long. So the humerus is 25 centimeters long. If we go over here and look up humerus, humerus 25 is right here. So we can make a prediction, and we would get on the blue line, once again, that it's right about here. Now we know that this green line right here, because every tick is 0.4, that is 22.2. So if I had to estimate, I would say 22.1 centimeters. And that would be it. Well, there you have it. Unit number 3, Exploring Linear Relations Review, using the Explain Everything app. Hopefully this video was helpful. Leave your comments below. I'm the math coach saying, thanks for watching, and see you next time.